Assalamualaikum dan salam sejahtera kepada semua yang menonton webinar pada pagi ini, sama ada melalui Webex ataupun menerusi FB Live. Terlebih dahulu, saya Najwa Nisara Masaad, Pegawai Sains selaku Moderator mewakili Pusat Pengurusan Makmal Universiti UTM Johor Bahru, ingin mengucapkan selamat datang dan terima kasih kepada semua kerana dapat bersama meluangkan masa menonton webinar Bicara Pakar UIRL 2021. Untuk makluman semua, webinar ini diadakan secara bersiri dengan melibatkan penceramah yang telah dilantik dalam kalangan ahli akademik dan pendidik UTM sebagai pakar bidang di makmal berpusat UIRL. Untuk webinar siri pertama, ianya terbahagi kepada 4 slot dan setiap slot dikhususkan kepada seorang pakar bidang yang telah dilantik mengikut makmal UIRL. Perincian lanjut bagi 4 slot berkenaan adalah seperti mana yang terdapat pada poster utama yang telah dihebahkan secara rasmi melalui email, website dan Facebook rasmi PPMU. Oleh yang demikian, seperti yang dijanjikan, hari ini pada tanggal 17 Ogos 2021, slot pertama webinar Bicara Pakar UIRL 2021 ingin berkongsikan satu tajuk yang sangat menarik iaitu Particle Size Analysis, Principle, Method and Application. Sebelum itu, saya ingin mengalu-alukan kehadiran penceramah hebat selaku pakar bidang makmal mass spectrometry iaitu Teknologis Dr. Norhayati Mohamed Noor, Pegawai Pendidik di Institute Pembangunan Bioproduct IBD UTM. Jutaan terima kasih diucapkan kepada Dr. Yati kerana sudi meluangkan masa untuk berkongsi ilmu dan pengalaman kepada kami semua pada pagi yang mulia ini.
Kepada semua penonton, webinar ini akan berlangsung selama 1 jam setengah dan selepas itu akan diadakan sesi soal jawab. Tuan-tuan boleh kemukakan soalan di ruangan komen di Webex atau FB Live dan saya akan bacakan soalan tersebut kepada penceramah kita nanti. Untuk makluman, link kehadiran untuk mata CPD dan UTM Akad akan diletakkan di ruangan komen selepas 30 minit sesi perkongsian ini berlangsung. Diharapkan semua penonton dapat terus setia bersama kami sehingga tamat webinar. Sebelum saya menyerahkan pentas maya ini kepada penceramah kita, marilah sama-sama kita mengenali terlebih dahulu secara ringkas latar belakang siapakah penceramah cantik manis yang ada bersama kita pada hari ini. Teknologis Dr. Norhayati Mohamed Noor merupakan pegawai pendidik di Institute Pembangunan Bioproduct atau IBD UTM. Bermula sebagai penolong pegawai pendidik, lantikan kontrak pada tahun 2004, kemudian menjadi pegawai pendidik kontrak, lantikan tabung IBD pada tahun 2006 dan akhirnya dilantik sebagai pegawai pendidik lantikan pada tahun 2008. Beliau memperoleh ijazah kedoktoran dalam bidang farmaseutik dari University College London, UK dan menamatkan pengajian beliau pada September 2017. Kajian PhD beliau adalah Lipid-Based Nanoparticles for Tropical Delivery of Hair Growth Therapeutic Molecules. Dr. Norhayati juga telah menerbitkan beberapa artikel berimpak tinggi dan bertaraf Scopus, penulisan bab dalam buku, prosiding serta pembentangan di persidangan bertaraf kebangsaan dan antarabangsa dengan memiliki nilai H Index semasa 5. Dengan tidak membuang masa lagi, saya menyebut penceramah kita, Dr. Norhayati untuk memulakan sesi perkongsian beliau. Dengan segala hormatnya dipersilakan.
I'm going to share with all of you based on my a bit experience on the particle size analysis, on the principles, methods, and applications for those who are working in this kind of research. So this could be one of your research area that you are focusing. That could be one of your potential for those who are not really joined or haven't experienced in this kind of analysis, might be can give you some idea for you to start or to plan your research that can be used in your research study. So for this topic, I would like to just focus on the dynamic light scattering techniques because as you know, the particle size analysis is really huge and wide and a lot of techniques can be used to measure the particles, right? So for these courses, I just will be focusing on the dynamic light scattering techniques, which is we call as a DLS techniques. But before that, I just give you some idea. So what I'm going to cover for these sharing sessions. So I'm going to introduce a little bit on the particles. Okay, what is particles? Why we measure the particles? When we should measure the particles? And also I will just touch a little bit on the principle of the particle size characterizations. Okay, and then the applications. Okay, for those who are working with the nanotechnology and also the microtechnology, the particle size is quite really important for you to measure the size of particles, right? And also I'll be going deep on the dynamic light scattering techniques and also the interpretation of result that I've been uh, get from the previous study. All right. So next we move to this particles. So what is particles actually? Okay, for those who are new in this area, so might be this is a good for you to see that this might be a potential for you to incorporate this kind of research, to incorporate this kind of analysis in your study, right? So the particles can be basically can be divided into the solid particles, right? And then the liquid droplets and also gas bubbles. All right. So a particle within physics is defined as extremely small unit of matter of substance. So means that from a matter or substance, we get a very subunit of matter, and we call it as particles, right? Despite the small size, a particle can still be assigned properties including volume and density. So even though the size is very small, like a nano range, 2 or 3 nanometers, still still have the volume and also the density. So this is we call as particles. Okay, for example, like powders, granules. Okay, this is kind of a solid particles like a pigments, like a paint, all right, and then the cement, and also some pharmaceutical ingredients. They can be in the solid particles, right? For example, for the liquid droplets, such as suspensions, emulsion, and slurries. For example, now is famous with the COVID-19 vaccines. Okay, some of these COVID-19 vaccines, they use a lipid nanoparticles to carry the DNA, to carry the mRNA. So you have to measure the size of particles, right? And also for the milk, okay, the mining muds for that industry. So this particle is not only one section's area, it can be very broad and very huge area. And the other example is aerosol and sprays. For those like having an asthma, so their inhalers having this kind of particles with a certain range of particles, so that the ingredients, the drugs can be target to their lung area, right? And also for this agriculture, they use this kind of particles research for the biopesticide in nano fertilizer to get a very small of this kind of particles, right? So why people are like looking for this kind of particles, right? Because we know that with a big size or large size having a very small surface area. So when they reduce the size of this kind of particles, the surface area become larger. So there's a lot of mechanism. There's a lot also things that relates when the size of particle is smaller. Maybe it can enhance the reactions for those like working like in catalyst. Okay, for those working in the pharmaceutical area, right? In for particles which is a smaller size, it could help to enhance the delivery of these particles. Maybe it can help in this because for the pharmaceutical or biopharmaceuticals, a lot of drugs, a lot of ingredients, the active ingredients is in oil phase. It's really difficult to dissolve in water. So in order to have this kind to improve the bioavailability of that kind of particles, the ingredients, to be absorbed in our body, or maybe to have like a longer time stay in our body. So they start to reduce this kind of particles, having like a nano range of size and maybe the micro range of size. So this is like a basic particles that you can find in our life. Okay. Then when we have this kind of particles, so let's say you have formulate products, you have doing some research on the particles of some of you might be facing particles in the reactions, or maybe you are formulating these products that have this kind of certain range. So you have to characterize these particles. So is it really in that range that you want the particles products, right? For example, you have to measure the particle size, okay, the particle shape, right? The particle shape also influence the maybe the reaction of the particles in the as a product. Maybe the shape of this kind of materials will effect on the release of the drugs, all right? For the surface properties, okay, some of these particles, they have attached some of other components. So in that also you have to characterize in terms of their the surface, right? And mechanical properties, for example, like stability, is it particle is stable at high temperature, low temperature, right? And for example, like lipids, nanoparticles, is it stable at a very temperature in Malaysia? For example, we are having like hot and humid temperature. So this is kind of the characterization that you have to do once you involve in this particles research, right? And then the charge properties of the particles. So if the particles is neutral, what happen if it uh, for the drugs or the formulation in the pharmaceutical? What happen if it attached to this kind of cells? Okay, do we need a positive charge of particles? Do we need a negative charge of particles? So this is kind of things that you have to characterize when you deal with particles. Same with the microstructure. So based on these characterizations, you have an idea like how your particles behave, right? But for this sessions, I'm just focused on the particle shape, which is we are focusing on the particle size analysis. All right. All right, next, why we measure particle properties. So you have your products, right? You have your products, you plan. So let's say if I give you some examples, you are producing products, maybe lipid nanoparticles or maybe some nano emulsions for skincare. Because what I will give you idea, like the things that I'm doing the research, because most of my research target on the topical delivery. Okay, so it's basically on the skincare products, the hair care products, how to produce a products to deliver for the skins. So I have to measure the size of particles. Okay, for my area, right? So for the skincare area, we do not want the ingredients, we do not want the particles to penetrate into the systemic or the bloodstream. We don't want it happen. So we have to characterize this kind of particles, especially the size. And then we also need to do another experiment to make sure that the particles is not transport, is not permeate into your bloodstream or your systemic. So this is the safety issue that you have to think, because even though it is because some people say the smaller the better, right? But it depends on the research area. If you are working with something which is very small, like a nano rods, carbon nanotubes, you really want it in a very small, like a 10 nanometer, like a 5 nanometer. That's okay for that research. But for another research, you have to study further. How is your range? What is your range for your particles? Okay, is it suitable in your research area? Okay, because there is a concern on the safety issue on these particles, or their size of particles, right? So yes, so when we measure the particles, so it is like to have like we can put our product in the higher premium products. For example, some of these cosmetic manufacturers, they are making a simple emulsion for skincare, like lotion, cream. But then when they see the trend for this nanotechnology, nanoparticles is expand, right? So then they try to incorporate this kind of active ingredients having these nanoparticles. So then they can put their products in the higher level with the premium premium range. So this is how they can use this kind of a study to put your product in the higher range. And then we also need to measure the particles to reduce customer rejection rates and lost orders. So this is basically on the production part. So if you are producing this kind of nanoparticles for skincare products, so you have to do a routine analysis to check the size every batch that you are producing the ingredients. So is it having the same size every batches? Okay, because sometimes when you formulate your formulations or your products, your nanoparticle products in the lab, having a very small scale, like a 10 mil, sometimes they are producing like 100 ml of products. But then when they want to upscale this kind of nanoparticles productions, okay, sometimes they couldn't get the same results because when you use the bigger size of equipments, they will give a different kind of study. So then you have to do some troubleshooting, some study to get the what's the maximum or the optimum condition for your parameters. Because for the particles, so it's related to this production as well. Okay, if you are using different kind of equipment to produce this kind of particles, they will give you different results in the size. All right. And then we also to measure the particles to demonstrate the compliance in regulated markets. So I can give you some idea for this kind of regulated market, especially on the nano materials. Right, so nanomaterials is something or particles which is having a size from 1 to 100 nanometer. Because this is like a general term that overall worldwide use for the nanomaterials term. So which is having particles from 1 to 100 nanometer. For this kind of materials, there is some other regulation that you have to follow in your country. Some say that you have to do this safety aspect because when you are dealing with these nanoparticles, okay, the safety issue might be quite important. For example, if you are doing some nano pesticide or nano fertilizer, when you dispose this kind of nanoparticles into the drain, into the river, what happened to this kind of materials, which is what happened to the environment? So this is kind of still um, issue that they are still questioning and also discussing among this group of people. Okay, even Malaysia also has a nanotechnology or nano Malaysia. They use this kind of they try to have some regulations to prove that this is nanomaterials to get the certification. Okay, this product is nanomaterials. Okay, then they will have some few safety regulations that producer or manufacturers need to follow, right? So then why we measure particle properties? So better understanding of products, ingredients, and process. So it can also improve our product performance. For example, in the skincare or the products for the topical applications, when you produce a nanoparticles and then you include in the nano in the products, they will give you different type of products. Okay, for cream, lotion, the normal cream or lotion, they are having size in the micron. Okay, but when you reduce the size to have like nano emulsions, so the properties of these ingredients might will be different. It will become more smooth, and then it will become less grittiness of the product, so it will improve your product performance, right? And also it can troubleshoot manufacturing and supply issue. For example, you have if you are a cosmetic manufacturer and you just buy the ingredients, which is the nanoparticles of active ingredients. So this is one of the good thing that you can measure this kind of ingredients that you get from the supplier to make sure that what they claim this product having this kind of range of particles is the same as you receive at your factory. Okay, and also it can increase output or also improve the yield of the products. All right, so we move to the particle properties. Okay, particle size measurement is routinely carried out across a wide range of industries. So like I said before, so it depends on your area of application. So it's quite a critical parameter in the manufacture of many products. Okay, particle size and shape have a direct influence on material properties such as the reactivity or dissolution rate. For example, if the particles is a catalyst and you are reducing the size of this catalyst, so it might influence the reaction time or dissolution rate of the drugs. For example, this kind of nano ingredients you incorporate into the oral like a dosage form or for oral intake, so it might affect your dissolution rate, how the drug dissolve in your body, right? And also these particle properties also affect in the stability in the suspensions, right? For example, in the sediments or paint, some of these particles, it if the products if the particle is quite it's quite dense, so it just sediment into your products, right? And then also these particles also affect on the efficacy of delivery of the asthma inhalers, for example. Okay, for example, for the asthma inhalers, they have the certain range of this kind of particles. They can't have a very small 100 nanometer size of particles, because if you inhales, the particles might go into your body. At certain size of these particles, it just stay on your lung. But if the size is very small, it just come out with your breathing. So this is why we have to characterize, especially on the pharmaceutical area. Particle size is very important for them to measure the size. And then also the appearance, the powder coatings and the inks, right? So the smaller the size might improve the smoothly of these coatings, right? And then the flowability and handlings, for example, like granules, okay? And also these particle properties also affect on the viscosity. Okay, some of the nasal sprays, okay, you can have very thick or dense, viscous nasal sprays because it couldn't come out from the bottle. So they have to control this kind. So when you reduce this kind of size, the viscosity might be also affected. They will just reduce, right? And also the packing density and the porosity of the ceramic, right? Okay, then we move to the particle size and shape in biopharmaceutical. Alright. Okay, the particle size and shape can influence a large variety of important physical properties like manufacturing, processability, and quality attributes. So this is like I mentioned before, the dissolution rates. Okay, basically most on this pharmaceutical area, the dissolution rate is quite critical parameter that they want to measure the bioavailability of the active pharmaceutical ingredients when they take this kind of drugs, right? The medicines, and also the drug release rate for the sustained and controlled release formulations. So this kind of nanoparticles or the microparticles they can having the certain size of particles, and they can manipulate this size to control these particles so that it can just release in your mouth if you want it, just release in your mouth, or maybe you want the formulation, the products, the medicine release in your stomach, so then they have a coating having this kind of particles. Okay, so this is some like research that they are doing, and to measure the particle size. Also, the in vivo particle distribution and depositions, when they do a research on the in vivo, especially on the rat, on the mouse, so they can see the how well the particles, even nanoparticles or microparticles, can distribute and deposit in targeted area, the absorption rates, the clearance time. So this is what they will study from the particle size that they have from the machine. The content and dose uniformity and other properties related to physical chemical stability, because some of the particle is not really stable, so they have to incorporate another ingredients. So it depends. Some they try to optimum the formulations ingredients, the ratio of this first ingredients and second ingredients. Sometimes they try to improve in the term of the processing parameter of the equipments to control the pressure, that basically the normal nanoparticles in basically in the biopharmaceuticals, to produce large scale of nanoparticles, they use like high pressure homogenizer to get a small and a small size with very narrow size distributions. So this is a kind of the condition that they will optimize to get the optimum size of your targeted area. Aerosolization behavior, flow and packing properties, and a grittiness of solid particles in chewable tablets, so dermal ointment. So this everything will affect the products based on the size and also the shape of the particles. Okay. Okay, then we move to the next one. Okay, so this one I just give you some basic idea. For example, in the biopharmaceuticals, okay, how the size of particles affect the delivery of these products to the targeted area. For example, like the oral, which is in granules, the target the size around 1,000 micrometer. But for those working with the transdermal, they want the drugs to transport to permeate into the systemic. So they try to produce particles having a size like 0.1 micrometer, which is like 100 or maybe less than that, maybe 200 nanometer or maybe like 300 nanometer. So it depends on the application of these particles. So if you have this research, this kind of research, so you have to know that what range you have to get your result. Then you can do your study based on that targeted area. Right? For example, now, like I mentioned, the COVID-19 vaccine, okay, they use the lipid nanoparticles, some of these vaccines. So they try to put another ingredients so that the product is stable, that can carry the mRNA and then can transfer into our what we call as intravenous, because we inject the vaccine into our body. So this is kind of the study that they focus, which is just small part of the study that you have really need to consider, to take into account that particle size is really important when dealing with these particles. Okay. Okay. The purpose of particle size analysis. Okay, normally people say that, okay, what we get when we do a particle size. Okay, so we can have the quantitative data on the mean size, particle size distribution, and the shape of the compounds to be used in a pharmaceutical formulation. So for those who are working not in the pharmaceutical, so you can use this kind of data to find your targeted size of your area, right? So if you have the quantitative data, okay, so you know that this size is used or is it out of your targeted range. So this is very important data that you can get, okay, and also the distribution of the particles, how well the particles distribute in your products. Okay, either the particles having very small sizes and then they have another population with a big size, or you have like very narrow distribution having very small sharp peak of just one sizes. So this will give you important result to see how well your product behave in your products. Okay, and also some of them they can get an idea is the shape of the compounds. Okay, for example, like people working with particles which is not sphere. Okay, you are working with something which is like nanorods. So this will give you some idea how well your particles shape in the formulations, right? So the particle size analysis also required to assure the quality of the final dosage form and the drug delivery system. Okay, this is one of the good thing that if you get the result of the size, so you know that the quality of your final dosage form, so means that your size is still within in that range. Okay. So then I just moved to the applications of this kind of equipment, the DLS equipment. So mostly people or researcher working in nanotechnology or microtechnology, or sometimes working in the industry producing milk powder, like a food industry, also use this kind of analysis. Okay, so why can I say that nanotechnology is a science, engineering, and technology conducted at the nanoscale, which is about 1 to 100 nanometers. So this is like a general term that they use. So whatever size less than 100 nanometer, they call it as a nanotechnology. All right, but sometimes it's just overlap with the other colloid science. So we have another research that working in the colloid science, saying that the nanoparticles or nanomaterials will have a size from 1 to 1,000 nanometer. So for myself, I'm working with the topical application for the skincare. So I don't want it to be 100 nanometer for my delivery of this kind of ingredients. So I want it to be in the 200, 300, maybe less than 600 nanometer, so that it's still considered as nanoparticles in a certain research paper based on the colloid science of research. So this is some of the term that could be some people not accept. They say, okay, nanoparticles should be less than 100 nanometer, then they call nanoparticles. But this kind of group say that, okay, we are working with nanoparticles, but I'm working with 200 nanometer, but I'm still saying this is nanoparticles. So for me, the particles that I'm working is in the size range of more than 100 nanometer, but I'm still saying this is a nanotechnology or nanoparticles or nanomaterials because it's still less than 1,000 nanometer. So if the particle is more than 1,000 nanometer, then it start to be called as a micro technology. So having sometimes working with the bacteria with having 1 micrometer, okay, having working with okay, virus, because the size of virus is in nanoscale, 10 to 150 nanometer. So they try to formulate ingredients to formulate the particles having this kind of sizes to set so that it can attach to the virus. So it depends. So whatever it is, it depends on your applications, right? Okay. So this is some basic application of nanotechnology, right? Nanotechnology in the market. So it can have like nanotechnology in electronics. Okay, you can have in the chemical manufacturing, producing materials, Okay, it can be in the energy, in the solar, some they call a nanographene to produce in this kind of particles in aerospace and defense. So in the healthcare, for example, in the pharmaceuticals, in the wellness industry, in the skincare. So this is quite a broad, okay, technology that can be used, particles or nanoparticles in this study, right? So it can offer benefits such as the compact effect, the higher efficiency, the lightweight. Okay, for example, materials that you are producing having very small size of particle, but with a bigger surface area, the 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 materials might be light compared with the mother of the substance, right? And maybe it can improve in the energy conservations and many more. So this is quite a broad technology that you can do research based on the particles, all right, study. So this is also some of these. I got these slides from the previous talk. They said that in Malaysia they also have a action plan for the national graphene. So this is basically on the solar part, all right? So, but the nanotechnology in Malaysia is quite good, especially in the food and agriculture, electronic devices system, energy and environments, and then also the wellness, medical and healthcare. So this is like quite broad nanotechnology that has been implemented even in Malaysia, right? So we are not like stay at the back. So a lot of people are focusing on the nano technology currently. So when we talk about characterization of nanoparticles, it's quite challenges, right? So because different disciplines are having different kind of targeted area. So for example, the interdisciplinary nature of the field. For example, people working with healthcare, in the pharmaceuticals, their targeted area is different with the people that working with the electronic, the graphene. So this is a challenges because there is no like suitable reference materials for the calibrations of the analytical tools. For example, you are sending this kind of products on these equipments. That equipment doesn't have different kind of discipline field. So this is quite tricky. Then and I know there's a lot of research still going on in this nanoparticles research, right? And also the difficulties linked to the sample preparation for analysis. Some samples is really difficult to do the preparation. Maybe you have to do some dilution, so you have to do some other optimizations in term of the sample preparations before you can measure your size, and also the interpretation of the data, because once you put your samples into that equipment, okay, that equipment will just run on their own. All right, you can just key in the data. Some data is really important, and then they just give you the data. So the problem is how to interpret the data. You will get a lot of data. So how to get the data and which one you have to choose. So this is come to the interpretation of data. So it's quite challenging, but still you have to take into account this particle size is really important in your study if you are working with the particles, right? So which particles characterization techniques do we need, right? Which particle properties are important to me? So what particle size range do I want to work for? So first of all, you have to know that which range of the particles that you are producing, either in the nano size within less than 1000 nanometer, or you want is less than 100 nanometer. So what is your target size? And if you are working with micron, so you have to make sure that this kind of info as a first things that you have to do before you proceed with the next experiments. All right. Okay, are my samples polydispersed? Do I need a wide dynamic range? For example, if you are producing, I just say that COVID-19 vaccines. So if you're really think that the size should be very small distributions area. So you have to make sure that in your productions, you have to make sure this kind of samples is having this kind of range. So means that once the second batch you are producing having a big size of the range, so there must be some incorrect way in your production of your product. So this is like things that you have to bear in your minds. So my sample polydispersed, or you just don't care about the polydispersity of the size of the particles. So it depends on your research area. So how quickly do I need to be able to make measurements? So based on my previous study, so I'm working a lot with DLS because I'm working with the size with 200 nanometer and above, but less than 500 or 600 nanometer, right? So the equipment that we use, like I say, the DLS, is not really uh, um, it's not really hard to do, but in terms of the interpretation of the data. So how quickly? So when I put the samples, put the informations, and within like less than 5 to 10 minutes, you can get the results. So this is quite important if you are producing formulations. So let's say in my study, I have to do formulations, and my first thing that I will check is the size of the particles. All right. So if the particles I'm having a very really high or a large size, I need to do something with my formulations, ingredients, concentration, or maybe in terms of these processing parameter. So this is things that we need to be considered, right? Do I need a measure a high resolutions? So if the product is really difficult to get, so how difficult you get the results, right? Do I need a good statistical sampling for the robust QC measurement? Because when you do pharmaceutical area, so they are really tough. Okay, they have a lot of standards to do a QC measurement. So you have to do every stage to check the size. So do I need to disperse my sample, wet or dry? So if your samples is nano emulsions, so is it in the liquid form or the powder form if you spray dry? So which one you need to choose to check the size item, okay? And how much money am I prepared to spend? So this is kind of that we have to think in our mind when we doing this kind of particle analysis. All right, so next, how do we define particle size, right? So if you working with the particles like in pharmaceutical or biopharmaceutical, they are working a lot with like liposome, nanostructured lipid carrier. They are working with something which is like a micelle. So a lot of this kind of materials in a sphere. Okay, so particles are three-dimensional objects, but unless they are perfect sphere, like emulsion or bubbles, they are perfect sphere, right? So they cannot be fully described by a single dimension, such as radius or diameter. So in order to simplify the measurement process, so mostly they just feel that the all material is sphere, so that they can convert the informations of these particles into a volume or mass examples. From this volume or mass, they can have information, the size of particles. So this is kind of theory that normally in the particle sizing analysis thing that all theory, all the particles is a sphere theory, right? So, and also it's important to realize that different measurement techniques use different equivalent sphere models, and therefore will not necessarily give exactly the same result for the particle diameter. So different particle sizes having their own algorithm, having their own models to convert from this kind of results, informations, and get the size of particles. So that's why when you compare from this kind of equipment to the other kind of equipment, sometimes you have like a variations of the particles size. Okay. All right, particle sizing methodology. So there's a lot of equipments, okay, that can be used to characterize the particle size. For example, in the atomic force microscopy, the transmission electron microscopy, or SEM, scanning electron microscopy, and they also use the scattering techniques such as dynamic light scattering and also the laser diffractions. But for first two, is a microscopy based techniques. So you can have an idea on the size of particles. You can see the particles, the morphology of the particles, and you also can know the structure of the particles. Is it a crystals? Is it in a amorphous system? So this is some things that when you do a particle size measurements using DLS or laser diffractions, you have to do another additional measurements. For example, TM. So in my study, so normally when we check the size of particles and we get the size of hydrodynamic diameter and we get the distribution, the particles, then we need to confirm with normally TEM, transmission electron microscopy, so that we know that, okay, this size of particles is not really far from this TEM. So when you get the sample, which is far different with each other, so then you know that how your particles behave, right? So sometimes you get the size in the DLS is smaller than the morphology from the TM. Some you get the size, the bigger size, and then you can know that how your particles behave. Okay. Okay, this is like a principle how the dynamic light scattering technique. So we move to this the topic that we really want to focus on, which is it use non-invasive and sensitive techniques to measure the size of particles in suspension and molecules smaller than a micron in the solutions, which is 0.3 to 10 micrometer. It's Melvin synthesizer nano, but based on the current works, they say that if the size is less than the size should be less than 1,000 nanometer. So you still can use the DLS machine, right? So that you can follow the few algorithm, the models that they have. Okay, but if the size, if particles is bigger than 1,000 nanometer, DLS is not really suitable for your study, right? So what happened is the laser is shot through a polarizer into a sample and the light is scattered. So what happened is if the laser, okay, pass through the samples, all right? So the sample has particles, okay, having different kind size of particles. Then they will have a scattered directions. They will go different directions, right? So this scattered light enters another polarizer where it is collected by photomultiplier and the resulting image is projected into the screen. So you can see once you start the measurements of the size, so you can see how well the fluctuation of your particles. So the process is repeated. So it takes many times, and the set of speckled patterns produced are analyzed by an autocorrelator that compares the light intensity of each spot over time. So what happened is they used a light intensity. So for, I can say this one, for dynamic light scattering, what happened is if you are working with particles, then the light pass into the particles, it will scatter the lights. Okay, for the smaller particles will have a greater scattered compared with the bigger size. So this come with this model that they use in this kind of equipment. So because they know that the particles, the small particles, when I say DLS is for the small particles, nanoparticles, less than 1,000 micrometer, they have their own movement we call as a Brownian motions. So means that they are not stay on the same place. They are moving. So these are a natural motion that they are being in these colloidal solutions. For DLS, only can measure the size of particles in suspensions, in the liquid form. Okay, you can put your powder form into this equipment. So you have to, maybe you can have to dilute in a water, or maybe you can do another equipment to study the size of particles for the powder products. But for those working in the liquid and having a size less than 1000 nanometer, yes, DLS is quite acceptable and quite famous that used for particle size measurements. So they use this kind of equation, which is the Stokes-Einstein equations, that they assume that when the particles is moved, so you can imagine that the in your formulations you have small particles, you have the particles, the large particles. For the small particles, they will move very quick and fast compared with the particles having a big size. So the movement is slow compared with the small size. So when you see these equations, so they can use these fluctuations or the movement of these particles convert into this equation. So they say it's a diffusion coefficient. So when the particles in liquid form in the suspension, so you have the particles in the samples, so it will move. We call it a diffusion, right? How they diffuse in this in these materials. So they convert this as a velocity of these particles, then they put it into these equations. So this equation will be calculated, automatic will be calculated from that machines, and we know that from this diffusion coefficient, which is the movement, the diffusivity of the particles, you can get the result of the hydrodynamic diameter. So for DLS, all the results we call as a hydrodynamic diameter, because the particles in a liquid form, in what particles appear can be diffused in a solvent form. Okay, so then they can convert into the hydrodynamic diameter. So this, you know that your particles having this kind of size. Okay. Okay, this is some roughly how the measurements can be done using the dynamic light scattering techniques. So you can see here from the particles, if your particles having like two types of sample cost, large particles and the small particles, so it give you different intensity size. All right, so the cost particle having like the small particles move faster, they will give a very sharp and a peaks compared with the cost particle. Then from this intensity, they convert into this autocorrelation function, which is everything is done by the machine. Okay, you don't. That's thank God that we do not need to do manually. So it just convert from that machine. But we can see from that machine, once we start the machines, when we open the machines, we can see that how well the particles behave. So for particles which is have very small particles, you can see the peak is very sharp right here. You can see here. But for the particles having a large size, the peaks, the gradients is like a larger, is far from the y-axis. So from that result, you can just roughly can guess is your particles is really having a small distributions or is your particle is having a large size. So then from this correlator, diffusion coefficient, they convert into that the equation. You can get the graph, okay, for the small particles having near to the y-axis, okay, and then the coarse particles having at the back axis. So this is we call as a hydrodynamic diameter, or we call as cumulant overall mean, because you can imagine in your sample you have maybe billion of particles, so they accumulate everything, make as algorithm and get everything and give you the mean of your all total of your samples, right? From that result, you know the PDI or polydispersity index. Okay, this is also important in your study. The PDI, how well your products behave, how well distributes in your formulations, the peak from intensity distributions, and also the width of the intensity distributions, the volume number, and also the number distributions. So this is some of the information that you can get from dynamic light scattering result. Right. So there is also some advantages and limitation of this. Includes the advantages, we know it's very quick, easy, and precise operations for monomodal suspensions for your products, which is target on the very small, narrow polydispersity index. So this DLS is really important in your study. So it's also really sensitive. Okay, it is reproducible for the monodispersed and homogeneous samples. So that's why when you do particle size analysis using DLS, certain concentration of the particles you have to optimize so that you can get the correct the results. Okay, for example, if you have a very concentrate of particles of your formulations, so the particles will have like multiple scattering, so we do not want it to happen. So what happened normally for the DLS measurements, okay, you have to dilute your samples so that the particles is really like a single particles. And when the light is go through, it just scattered with their own. Not if you have like a very high concentration of samples, the scattered light won't go directly to the detector. It just go next to the particles. So that's why the concentrations of your formulations also important to measure the size of particles. But there are also limitation of DLS. Okay, the necessary conditions for the particles to be in suspension and undergoing Brownian motions. Okay, if your samples is powder form and you cannot dilute in water, then you can't use DLS. You have to use another machines, because we afraid that if your particles dissolve in water, the particles just completely dissolve and there is no particles that you can measure. Okay, you have to think that the DLS only measure the particles, not a solution, right? Like for example, a salt you dissolve in water. So it's just a solution. Then you cannot measure the size of particles, all right? Okay, and then the large particles scatter much more light and even a small number. So this is a critical point as well. If you are producing a product and then your formulation having very broad size range, one population having small and another population having big, large size, so the lights will like prefer to focus on the large the bigger size of particles. So it will give you some error, or I mean some not correct results. Okay, and also we have to make sure that this DLS, we need to assume that the particles is spheres shape. Okay, then we can use this kind of DLS. But sometimes if you are working with a nano rod, for example, which is having a cylinder shape, then they still can use this kind of machines, but then you can compare how well your products, how well your particles behave. Okay. Then when we do a research, when we do a particle size analysis using DLS, okay, I just focus on DLS. Okay, you can get many informations, okay, from the software. They will give you the intensity weighted distributions, the volume weighted distribution, and also the number weighted distributions. Okay, sometimes people which is not familiar with this um, research, they don't know which one to get the result, because different uh, distribution sometimes will give you different range of size. Okay, for example, for DLS, it is also it is like important. Normally, we get the size from the intensity. Okay, intensity weighted distributions. Okay, means that how much light is scattered by the particles. Okay, if the particles is the big or large size, and also if the particle is a small size, it just can have a mean for all sizes. Okay, this is like a most accurate and reliable distribution, and is closely related to the raw measurements that the instrument takes. So for DLS, normally we suggest to get the intensity result, but you still have the result from the volume weighted distributions and also the number weighted distribution. So for the volume, it shows the total volume of particles in the different size. Okay, so it just get the result from the intensity light, and then it computed using the algorithm that they have. Okay, and they use the refractive index of the solvents, all right, and convert into the sphere volume formula. Then they get a volume distribution result in a nanometer as well. And then also you can have a different result, which is particle size in the number weighted distribution. So mean that it is show the number of particles in different size. Okay, for the number, they give you the result which is the different size. Okay, so it depict a distribution that would be obtained from particle count 10 such as TM. So then you know that how your particles is behave in your products. Okay, but for DLS, normally we just focus on the intensity, because it just come from the intensity from the lights. Okay. Okay, particle size distributions. Okay, I will just talk a little bit on the Z average. So based for particle size analysis using DLS, you will get the result which is the hydrodynamic diameter. We call it is hydrodynamic diameter, and sometimes we call it as a Z average. Okay, Z average is not zeta potential, but Z average is the mean of this intensity result. Okay, so firstly, the results are based on light scattering. So due to the previously mentioned 6-power relationship between light scattering intensity and particles diameter, the larger particles dominate the signals. So like I mentioned before, if you have the non-homogeneous of the size of particles, the larger particles will dominate. So means that if you have the result from the DLS system, uh, the larger will have like dominate all your results. Okay, and DLS measures the hydrodynamic diameter, like I mentioned before, which is the diameter of the particles plus some ligands, ions, molecules, or other active ingredients with the surface and travel with the particle solutions. So sometimes people say that, okay, my sample size for this kind of particles using DLS having 200 nanometer, but then they check with the TM, because you can see exactly the particles, right? The morphology of the particles, and you get a smaller size of particles. So what happened is, normally people having this kind of arguments. Okay, they feel that okay their result is not correct, but then there is some important items that hydrodynamic diameter using DLS is a diameter including everything that come together with the particles. So if your particles having a emulsifier, if your particles having some surface coating, so everything is come together. Compared with the TM, like the pure size of the particles. So it different techniques that they use. Okay. So then polydispersity index. Okay, polydispersity index is measure of the heterogeneity of the sample based on the size. So what I mentioned before, so if you are producing nano formulations, so we really want the particles in the same size. Okay, for my study, but maybe some of you want it to have different kind of population of size. But for me, if I'm making formulations of this kind of nanoparticles, I'm targeting the PDI, polydispersity index, to be less than 0.3. Okay, so PDI is that like arbitrary unit. So the maximum is 1. And the smallest could be like 0.003. Okay, so if you have the p value less than 0.05, so which is very monodisperse, okay, means that every single size in the same size, you don't have the big size. Okay, 0.05 is really small. Even for my formulation, I am so difficult to get 0.05. But for me, I'm targeting to have less than 0.3. It's quite enough. Okay. Or some people say that less than 0.5. So it depends on your area as well. So you have to check with your applications. But for the ISO standards, they say that p value less than 0.05, you call as a monodisperse. But if value PDI is 0.7, so you have the polydisperse, means that you have many peaks of samples, so it is a broad size, right? So for I think mostly in the pharmaceuticals and formulations in skincare, we target to have PDI lower than 0.3. Okay. Okay, particle size distributions indicates that the sample has a very broad size distributions. So if you have result PDI is more than 0.7, so means that your samples is not suitable to use DLS to measure the size. Okay, so you have to use another equipment, maybe the laser diffractions. All right. Okay, I just gave you some example from my previous study. So I want to see the hydrodynamic diameter, okay, compare with the coating and without coating. So I can see that what's the difference. So when you can see from here, the hydrodynamic diameter giving you a size in a nanometer, okay, and you have to see the PDI as well. So PDI and hydrodynamic diameter is the main for me is a main information that you have to know. Okay, other than that you have to do the TM or another equipment to prove that okay your formulations, your particles is having this kind of sizes. Okay, this is, and I also will give you some nice result from the intensity. Okay, this is from intensity. Okay, to get this very nice sharp peak, okay, you have to optimize your parameter in terms of your formulation ingredients, in terms of your processing parameter, because my target is to get this PDI less than 0.3. Okay, so if you can see, we target to get 0.3, and then we have very sharp one peak of samples, right? But I know that a lot of people having a lot of problem to get this kind of the results, because you have to optimize everything to get this kind of PDI and also the size. Okay, but then sometimes we will face I think a lot of time I'm facing this kind of results. Okay, having like 2 peaks, or sometimes I have like 3 peaks, sometimes I have a very broad peaks. So this is the interpretation of your results. Okay, you can see the Z average. Okay, you have like 583, but then the peak size here is 1000. So means that this equipment is probably not really suitable for this kind of analysis. Okay, so then this is a research that when we do a research, this kind we will facing this kind of a result, right? Okay, so then I think this is my few slide before I finish. Okay, so when we say that, okay, there is 3 scenarios that normally will happen. The Z average is smaller than the peak size. Okay, maybe or Z average is the same as the peak size, or the Z average is larger than the peak size. So it depends on your materials, your products. Okay, for the standard normally that they use, normally they have the same, like exactly near to each other. The Z average same as the peak size. When I say the Z average and the peak size, you can see from here. Okay, you can see from here. Let's see. Okay, so this is Z average for this first result. Okay, and PDI is very small, 0.175, but the peak is 670. Why I have like intensity is 100%, but I'm still having the size 670, but I still have the PDI small and the Z average is 500. So it could be due to the small population which is here, that they still take this result to get the mean of the particles. So that's why my Z average is smaller than the peak size. Okay, so for example, like this one, if the Z average is the same as the peak size, so currently in my experience, I haven't get this kind of result, because mostly this kind of result comes from the standard, okay, the standard bits that they have when we calibrate the machine. Then we know that the Z average is really same as the peak size. So if the standard is 60 nanometer, the peak size is near to 61 or 62 nanometer, which is really near to each other. But in real study, it's quite difficult to get the peak size and the Z average as same as near to each other. And also some of them is Z average is larger the peak size, so it could be contribute to the larger size of the particles, which is not means that you cannot see from here, but still some of the particles having bigger than this range. So it just have everything together, get the mean. That's why your particles having the size average bigger than the size of the peak, right? So, all right. So then I think that's all for my sharing sessions. So if you interested to send your sample to UPMU, you can contact Atira Hanis, which is the person in charge for this analysis. With that, thank you for your attention.
Terima kasih Dr. Yati atas perkongsian ilmu yang sangat bermanfaat seperti tadi. Saya yakin ramai penonton kita telah memperolehi sedikit sebanyak tambahan ilmu baru, terutamanya para pelajar yang sedang membuat kajian dalam bidang yang sama. Ingin saya ingatkan sekali lagi kepada para penonton untuk mengisi dan melengkapkan link kehadiran yang telah diberikan bagi melayakkan saudara mendapat mata CPD dan UTM AKAD serta mendapatkan ECJ program. Okey, sekarang saya akan bacakan beberapa soalan daripada penonton kita melalui Webex dan juga FB Live. Okey, Doktor. Soalan pertama. How PSA have different function compared to TM and SEM analyzer?
Oh, okay. So, Okay, sorry. Okay, for the DLS, they use a laser. They use a laser to 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 go through the particles, and then the laser the light will be scattered. Okay, that's different with the TM. Right, the TM using a transmission electron microscope, whereby the photon is transmit to these the particles, and then the sample preparation as well is different. So sometimes they do both of this research study to compare this kind of results. So they do a DLS having this light scattering techniques, and they do also the transmission electron microscope, okay, to see the because they can get another information about the particle itself, because that is the real particle, the morphology. You can see the particles, what happened, the particle, is there any agglomerations, is there any aggregations happen to that particles. So that's why they are using different techniques, right, for the TM and also the DLS system.
Okey. Untuk soalan kedua, what are some of the fundamental characterization technique applied in the study of nanoparticles for heavy metal absorption?
For heavy metal absorptions, for this kind of materials, I think you have to do, because I'm not working with the heavy metals, but they do some research on the like gold nanoparticles, the silver nanoparticles. So what I suggest, they do some differentiation in terms on the concentrations when they send the samples. Okay, the different concentrations might give you some idea how your particles behave, right? Because some of these particles, like they are not scattered the light, so you have to do some optimum or parameters that you have to study in order to get which maybe the concentrations of the particles. Because sometimes when we get the samples, okay, when I say that you just have like a very clear samples, okay, and then you do not know how concentration that you want to use for your analysis. So that's why you have to do some preliminary, right? Either you have to dilute 1 to 10 ratio, or 1 to hundreds, okay, so that the light can be scattered overall, so that the particles itself is single, not in agglomerations happen.
Okay, untuk soalan ketiga, what usually cause cluster of nanoparticles? Is there any techniques to avoid?
A cluster of nanoparticles. So actually it depends on the many aspects. Okay, the formulations. Okay, in terms of your in the percentage of your ingredients that you use. Some of these ingredients you use has a certain limits. Okay, when you use more than that limits, okay, you have another cluster appeared in your graph. Okay, let's say this ingredients, I can just give you an idea. This ingredients is oil soluble, and then you want to make it in the nano emulsion, let's say. So you have to get into emulsifier so that it can just stay. And then some of this is emulsifier, they have a certain limit. Okay, when you add higher amount of emulsifier, because emulsifier sometimes they can be as another population of particles. They can have like a different micelles. So you can have sometimes two peaks of your results, which is not really your particles, but the result come from the ingredients, not your particles that you want you to target. So there's a lot of parameter or preliminary study that you have to do to see which one is the correct optimal in terms of the ingredients formulations, and also in terms of the equipment that you use. So you have to optimize as well. Okay, in terms of this, let's say if you are making some nano emulsion using ultrasonication methods, so that ultrasonication has a limited time. If you proceed more than that amplitude, maybe, or maybe the time, the particles start to break. I'm not really sure, okay, but possibly yes. Okay, because if you are working with nanoparticles which is very sensitive, right? You are using the lipids, you are using some ingredients which is not a metals. Okay, for the metals it's quite not because if you are okay, if you are working with the metals, gold nanoparticles or silver nanoparticles, okay, and also you still have some troubleshoot to do in your study. Which part you have to focus, formulations or maybe in the processing part, the equipment that you use to optimize. So I can't say just specific answer because it depends on your research area as well. Okay, am I answering the question?
Okey, Doktor. Soalan daripada FB. Assalamualaikum. Nak tahu cara to understand DLS result analysis.
Oh, okay. So I think I have mentioned before the result analysis. For the DLS, for me, I just give you a tips that always take the intensity result. Okay, that's my area. I mean, I will just focus on intensity result, but at the same time, I use the result from the volume and also the result from this number to get an idea how well is my particles behave. Am I producing a particles having just small populations? And then I can compare the result from the intensity with the number and also with this volume, right? So volume and number give you a very wide idea for your formulations. So don't just neglect the result, okay? Because normally Atira will give you the result from intensity, volume, and number. Then you can have an idea how well is your particle behaves from that result. Okay? See the PDI size, which is the Z average, or we call it as hydrodynamic diameter, because some paper, okay, they mention hydrodynamic diameter. So if it is hydrodynamic diameter, means that they are using DLS system, okay, whatever brand. And then see also the PDI as well. So this is the main two criteria that you have to put in your first when you screen your particles. So if you're working with the nano or micron, which is really important to measure the size first, and PDI as well.
Okey, soalan lagi. In term of agglomeration, how it can measure?
In terms of agglomerations, so normally people try to dilute the samples, right? Because sometimes the sample is just stay together, okay? And then you have the bigger size. But when you dilute the samples, so you can separate the particles. So then you can have like a correct size of your particles, right? So this is for the optimum condition of your samples preparation, okay?
Lagi, do we need to mix our sample with surfactant before the analysis in order to get better result?
So actually, it depends on your area. So for me, if I'm working with nanoparticles, and my last product will be a cream or lotions, because normally I will just dilute the sample with the same solvent that you use to prepare the samples. Okay, if you use the buffer, then you dilute with the buffer. If you use a sample with or DI water, then you dilute with DI water. So that's my experience. But it also it depends on your area as well. So if you want to add the surfactants, because some surfactants they produce a micelle system. Okay, sometimes it just improve the solubility of your ingredients. Okay, some surfactants produce another populations of the particles. So it depends. So I'm not really sure. Maybe it depends on the application as well, I think. Yeah, but for me, I'm just dilute the sample with the same solvent that I used to prepare the formulation.
How about microplastic study in applying this technique?
Microplastic study. So because I'm not working with microplastic, so I hope that the thing is the basic fundamental of particle is the same, right? So if you can produce your own nanoplastic, right, and then you can have this nanoplastic probably in a liquid form, okay, then you can measure the size, okay, but you have to put in mind that this microplastic having the size should be less than 100 nanometer. So if it is less than 1000 nanometer for the DLS, but if you are making larger size of microplastics, so you can use a different technique, which is the laser diffractions. Or maybe we can have another session for the laser diffractions study, which is for the micron size of analysis. Okay, I hope I'm answering the questions. I can't say, I can't hear you.
Okay.
Sorry.
In term of soalan yang terakhir, in term of heavy metal absorption, which kind of nanoparticles is the most preferred choice?
In term of, can you repeat? In
term of heavy metal absorption, which kind of nanoparticles is the most preferred choice?
I can't get the answer, but I'm or is she making like a gold nanoparticles or silver nanoparticles? Because for silver nanoparticles and gold nanoparticles, yes, they do and use this DLS system, okay, to measure the size, because the size is very small. Okay, DLS is quite good for measurement of the size. Yeah.
Okay, Alhamdulillah. Masa amat mencuri kita sebab dah 11.30.
Okay.
Maka berakhirlah sudah sesi perkongsian bicara pakar kita pada pagi ini. Sekiranya tuan-tuan memerlukan maklumat yang lebih lanjut, boleh menghubungi Dr. Norhayati di IBD ataupun pada website PPMU sendiri. Bagi pihak PPMU, Jabatan Ten CPI dan Jawatan Kuasa Webinar Bicara Pakar UIRL 2021, kami mengucapkan jutaan terima kasih kepada Dr. Norhayati Mohamed Noor kerana sudi meluangkan masa untuk berkongsi ilmu yang sangat bermanfaat untuk para pelajar dan penyelidik serta penonton pada hari ini. Terima kasih juga diucapkan kepada Jawatan Kuasa Webinar dan semua penonton yang terus setia menyokong dan menonton bersama-sama kami sepanjang webinar ini berlangsung, dari mula sehingga akhir. Kami juga ingin memohon kemaafan jika terdapat sebarang kekurangan dan kelemahan semasa sesi ini berlangsung. Kepada penonton yang telah berdaftar, mata CPD dan UTM akad akan diberikan beserta dengan ECJ program. Semoga kita berjumpa lagi di webinar akan datang, iaitu slot kedua pada 23 Ogos 2021 yang bertajuk Nitrogen Sorption and Isotherm Analysis yang akan disampaikan oleh penceramah hebat merangkap dekan Fakulti Sains, iaitu Profesor Madya Dr. Zaitun Abdul Majid. Akhir kata, jaga diri dan jaga SOP. Assalamualaikum dan salam sejahtera. Terima kasih semua.